Can you at a high level say what are the basic mechanisms of evolutionary computation algorithms that use something that could be called an evolutionary approach? Like, how does it work? What are the connections to what are the echoes of the connection to his biological
A lot of these
neighbor?
algorithms really do take motivation from biology, but they are caricatures. You try to essentialize it and take the elements that you believe matter. So in evolutionary computation, it is the creation of variation and then the selection upon that. So the creation of variation, you have to have some mechanism that allow you to create new individuals that are very different from what you already have. That's the creativity part. And then you have to have some way of measuring how well they are doing and using that measure to select who goes to the next generation and you continue.
So first, you have to have some kind of digital representation of an individual that can be then modified. So I guess humans, biological systems have DNA and all those kinds of things, and so you have to have similar kind of encodings in a computer program.
Yes, and that is a big question. How do you encode these individuals? So there's a genotype, which is that encoding, and then a decoding mechanism which gives you the phenotype, which is the actual individual that then performs the task and in an environment can be evaluated how good it is. So even that mapping is a big question then. How do you do it? But typically the representations are either they are strings of numbers or they are some kind of trees. Those are something that we know very well in computer science, and we try to do that. But DNA in some sense is also a sequence and it's a string. So it's not that far from it. But DNA also has many other aspects that we don't take into account necessarily, like there's folding and interactions that are other than just the sequence itself. And lots of that is not yet captured, and we don't know whether they are really crucial. Biological evolution has produced wonderful things, but if you look at them, it's not necessarily the case that every piece is irreplaceable and essential. There's a lot of baggage because you have to construct it, and it has to go through various stages, and we still have appendix and we have tailbones and things like that that are not really that useful. If you try to explain them now, it would make no sense. It's very hard. But if you think of us as product of evolution, you can see where they came from. They were useful at one point, perhaps, and no longer are, but they're still there. So that process is complex, and your representation should support it. And that is quite difficult if we are limited with strings or trees, and then we are pretty much limited what can be constructed. And one thing that we are still missing in evolutionary computation in particular is what we saw in biology, major transitions. So that you go from, for instance, single cell to multi-cell organisms and eventually societies. There are transitions of level of selection and level of what a unit is. And that's something we haven't captured in evolutionary computation yet.
Does that require a dramatic expansion of the representation? Is that what that is?
Most likely it does, but we don't even understand it in biology very well, where it's coming from. So it would be really good to look at major transitions in biology, try to characterize them a little bit more in detail, what the processes are. How does like a unit, a cell, is no longer evaluated alone. It's evaluated as part of a community, an organism.
Right.
Even though it could reproduce, now it can't alone. It has to have this environment. So there's a push to another level, at least of selection.
And how do you make that jump to the next level?
Yes, how do you make the jump?
As part of the algorithm.
Yeah. So we haven't really seen that in computation yet. And there are certainly attempts to have open-ended evolution, things that could add more complexity and start selecting at a higher level. But it is still not quite the same as going from single to multi to society, for instance, in biology.
So there essentially would be, as opposed to having one agent, those agents all of a sudden spontaneously decide to then be together, and then your entire system would then be treating them as one agent.
Something like that.
Some kind of weird merger built in. But also, I think you mentioned selection. So basically there's an agent and they don't get to live on if they don't do well. So there's some kind of measure of what doing well is and isn't. Right. And does mutation come into play at all in the process, and what role does it serve?
Yeah, so and again, back to what the computational mechanisms of evolutionary computation are. So the way to create variation, you can take multiple individuals, two usually, but you could do more, and you exchange the part of the representation. You do some kind of recombination. It could be crossover, for instance. In biology, you do have DNA strings that are cut and put together again. We could do something like that. And it seems to be that in biology, the crossover is really the workhorse in biological evolution. In computation, we tend to rely more on mutation, and that is making random changes into parts of the chromosome. You can try to be intelligent and target certain areas of it and make the mutations also follow some principle, like you collect statistics of performance and correlations and try to make mutations you believe are going to be helpful. That's where evolution computation has moved in the last 20 years. I mean, evolution computation has been around for 50 years, but a lot of the recent
success comes from mutation.
Comes from using statistics. It's like the rest of machine learning based on statistics. We use similar tools to guide evolutionary computation. And in that sense, it has diverged a bit from biological evolution. And that's one of the things I think we could look at again, having a weaker selection, more crossover, large populations, more time, and maybe a different kind of creativity would come out of it. We are very impatient in evolutionary computation today. We want answers right now, right quickly. Yeah. And if somebody doesn't perform, kill it. And biological evolution doesn't work quite that way. And
it's more patient.
Yes, much more patient.
So I guess we need to add some kind of mating, some kind of like dating mechanisms, like marriage maybe in there. So into our algorithms to improve the combination mechanisms as opposed to all mutation doing all of the work.
Yeah, and many ways of being successful. Usually in evolution computation we have one goal. Play this game really well and compared to others. But in biology there are many ways of being successful. You can build niches. You can be stronger, faster, larger, or smarter, or eat this or eat that, or So there are many ways to solve the same problem of survival, and that then breeds creativity, and it allows more exploration, and eventually you get solutions that are perhaps more creative, rather than trying to go from initial population directly or more or less directly to your maximum fitness, which you measure as just one metric.